Hey Team Fusion, alright, explain how to use the analog inputs on the Cypress board to bring in buttons and stuff, which are of course digital inputs. So I've designed a simple circuit, and I mean there really isn't much to it other than resistors and buttons, that harnesses the Cypress board's power supply, which comes from USB, and uses a single analog input. So for this demonstration, I have 8 buttons. And as you can see, they're really switches on here, but in your use, they'll be buttons. Just 8 buttons in between resistors, and then also a resistor down here. So let me kind of explain what's going on in the circuit. What you have right here is it's a series resistor network, starting from this point right here, which is 5 volts. All the way down to this point down here, which is 0 volts or ground, in a USB case. So if you kind of do the math, you have 8 equal resistors, 125 ohms apiece, which all add up to 1000 ohms, and you have 5 volts. So if you do 5 volts divided by 1000 ohms, you get about 5 milliamps. So that gives you a little bit of current going through the whole circuit, which will give you a steady voltage. And given that resistors, I think, are typically within 5% tolerance, I mean, you should get a value that's pretty close to 5% of what it should be. So I'm just going to dive straight in. I'm not going to worry about doing the math and figuring out the voltages here, because in real life, the voltages aren't going to be exactly this, and actually you're going to have to set kind of a range, and this range should be within the specs of the resistor. So if it's a 5% tolerance resistor, then you probably want to put a 5% tolerance on the voltage, plus and minus. If it's a 10%, you want to do plus or minus 10%. The other thing that I have going on here is just a multimeter set up in the simulation software. So you can see here, it'll give me the voltage that's currently being applied to this whole, I guess, leg of the circuit. And yeah, okay, I kind of lost track. Anyway, this resistor down here is also extremely important for your circuit to work properly. What this resistor right here does is it provides a pull down for the circuit. As you can see, it's on the ground side of your power supply, and it's attached to the input side of your Cypress board. In circuitry, analog sources or analog inputs need to have some type of a pull down or a pull up of some sort in an unconnected state. Otherwise, the voltage will literally float around. If I didn't have this here, the voltage would float around, whatever voltage is in the circuit, so anywhere from 0 to 5 volts, which will create an unpredictable state. So adding this 1 kilo ohm resistor as a pull down will pull the circuit really close to 0. As you can see, the last measurement was 3.35 nanovolts, which is extremely small. So I'm going to go ahead and start the circuit up again, and there you go, 3.355 nanovolts. So I can simply switch the circuit here and it'll go to 5 volts, because that's the, it's connected straight to the power supply, which is 5 volts. So there's your 5 volts. If I switch any of these other ones, it'll remain 5 volts, because there's basically 0 resistance going from this point to this point. Meaning that all the current from the power supply is going through here. None of it's going to be pulled down at all from any of the other ones. So that's kind of a, hey, you need to note this type of stuff, because if you're trying to use some type of combination of buttons to do a certain task, if this button's pushed down, you can't have any combination. I'll get to that in a second. Anyway, so I'll switch this back to an open state, and of course it goes back down to nearly 0 volts. If I click here, it's going to be pretty close to 5. It's not going to be exactly 5. But okay, so you can see it's right at 3.9 volts. If I click here, it should be about 3.5 volts. No, okay, 3.1 volts. And as I go down the switch circuit, the voltage is going to get lower and lower and lower. So right there is exactly 2 volts. Here, 1.5. I think this one was really close to 1. Yeah. And this one was like half a volt. So yeah, 563 millivolt is half a volt. As far as the combination of stuff, so you notice that this one here provided 2 volts exactly. So, and this one here provided about 1.5 volts. So if I put both of them together, it'll create a voltage in between 2 and 1.5, which is 1.75. It's kind of a cool feature, so you can have a combination of things. So I would not recommend doing this in competition because it can be hard to remember combinations. I would just add more buttons to the circuit. But it is possible to, if there is some type of like secret function or that only needed to happen at a certain time in the game, and you didn't want to add another button, you needed to push down these 2 buttons to activate it, you can do that. So now that I'm done explaining explaining how the circuit works, I'm going to kind of try to explain how to use this with the Cypress board. So the Cypress board uses USB power. It's 5 volts and it's limited to 500 milliamps. So picking at the resistance here, you just need to make sure that it's below 500 milliamps if you're only using that USB port. But you're going to be using the hub on the classmate PC. So you really want to keep this down to a really, really low current. So 5 milliamps, which is what this is set up for, will work great. This won't add any extra resistance really. I mean, if you have this and you have this, it's still only going to be 5 milliamps of current going through it. Because right here, in electronics, an ideal multimeter has a infinite resistance to it, meaning that no current flows through it. It's not exactly true. There's a very, very small bit of current that flows through it, but it's negligible. So now I'm going to try to explain some of the math on it. If you feel comfortable with the circuit, then by all means go ahead and wire it up. But I was gonna tell you how to how everything connects up to the Cypress board. So there should be a ground connection of some sort, which this would be connected to. There should be a power source, a VCC usually, which is what this will be connected to, and then you'll have an analog input. I can't remember how many there were, but you would connect the analog input directly to this whole line here. So anyway, alright, so I think I have a better solution for this. I have this cool ass desk that I have at my apartment, and and a wet erase marker. Really cool, right? Alright, so I'm going to attempt to do this. I already tested it, so it will erase. So this isn't a completely stupid idea. But anyway, what I'm going to try to explain. So you have the 8 resistors coming down. So call this one R1, R2, R3, R4, R5, R6, R7, and R8. Right? That's our 8 resistors. And we also had one additional one, which I will place right here. So draw kind of a space here and call this R pull down. And we said that each one of these is 125 ohms. So I'll just kind of leave that as a middle mark, so I don't have to mess up my whole desk for all this. Also notice that this one down here is just out of range. So what I'll do is I'll go ahead and place this wire coming up, and just note that that's where that's going to. This point right here is connected to your ground on your Cypress board, which is also in turn, you know, if you do the circuits and stuff, you have your power supply. So this is 5 volts, and this is also called your VCC. Don't ask me what it stands for, I really don't remember, but that's the standard. It's like I don't know, it's just your operating voltage basically. And then we had, at each one of these you had a switch. And coming off the switch, all the wires went to the right. And kind of connected there, went up, and this goes to your, of course, your analog input. On your Cypress board. Alright, so that's how the whole circuit's laid out. Now, this is all really cool, but it's also really complicated looking if you've never gone through a circuits course. You have no idea what's going on in the circuit. Seeing as it's just resistors, if you've ever seen a circuit board with a whole bunch of components on it, there are a whole bunch of different components. You never see a board with just resistors. Resistors are really easy to understand. So let me erase this real fast. I'm going to simplify the circuit. So actually, let me say we're going to find the voltage at we'll say this point right here. So if you do the math, you have 125 ohms here, and for series what you do is you add up all the resistances between the 2 points, which give you 875 ohms. So keep that number in your mind, and let me erase this real fast. Alright, so we have a clean slate again. Excuse me. Alright, so if you remember, we had that series resistor network, which we'll just label as one resistor here, and it was 875 ohms. Alright, then you also had that pull down resistor, which essentially can be placed right here, and it was 1 kilo ohm. Those two resistors, when you had the switch closed, are then connected together as such. And to keep everything in check, you know, that's your 5 volt supply. And then you also had that one resistor that was above the other 7, which was 125 ohms. So you simplify your circuit down, you're trying to find the voltage at this point right here. One of the things with circuits, to find the resistance, your equivalent resistance from here to here, so if you want to like take these two out and you want to just replace it with one resistance, use a simple equation. Basically it's 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R7, like however many you have. So, you know, with little dots there to say, you know, you can have as many as you want. Basically what this simplifies to, you can say it's 1 over R1 plus 1 over R2 plus 1 over R7. So you can kind of see where we're going with this. So if we want to find the resistance, your equivalent resistance from here to here, then you need to you know, put it into this equation here. So you say 1 over 875 ohms plus 1 over 1,000 ohms, which will be equal to, and, you know, just use a calculator for this. Keep it simple. And of course I'm going to use kind of like a little shortcut here for me because I'm used to doing this. So actually, I won't even do that. I'll just do simple. So 1 over 875 plus 1 over 1000, and you get 1400 over 3. You simplify that down, it's equal to 466.667, which you know is of course just, oh, I'm writing off the screen. This is equal to 466.66. You repeat it over. Still off the screen. I'm not even looking at the screen when I'm recording this. So 466.66 repeating over itself, so you just put a 7 there. So you can replace that resistance. You put that right there as your resistance. So then you simplify the circuit again. So let me erase my cool little board again, and I'll be back in a second. I just switched markers because it was getting a little hard to erase. So we came down that we had we still have our power supply here, which is 5 volts. This is gonna glare really bad. Turn that off will help. Ooh, that's perfect. Okay, ooh, you can see my face in it too. And then you have your ground down here, and then you have that one resistor, which was 466.67 ohms, and then you still had your other one, which was 125 ohms. So if you do the math, you add those two numbers together, which we'll do right here. So plus 125, your total resistance. So you add those two together. I'm gonna try a different color. My black one's kind of running out. So you add those together, and you get 591.667 ohms is the total. So then you want to find the current going through the circuit, and actually I'm drawing this backwards. Genius me. It doesn't matter. You want to find the current going through the circuit. So we know still that this is 5 volts. So let's do 5 volts divided by 591.667 ohms, which is 8.451. Ah, dang it. Alright, I guess I have room up here. So do 5 over your 591.667, which is equal to 8.451 milliamp. So that's the current going through the circuit now. And you want to find the voltage at this node in the center. So really, you can say, what's the voltage between here and here, and you're looking for the voltage. So you just need to find the voltage going across this resistor. The bottom of it's 0, of course. So it's going to be really simple. So again, to find your voltage, you use V equals IR. I'm going to erase some of this stuff. So let me write down the 8.451 again. Just it's memory for me. Erase some of this stuff. I should erase everything. I should have used this marker to begin with. It's a lot better. Excuse me again. Alright, so we had try to write this over. 8.451 milliamps. And you had 466.667 ohms in the bottom section of the whole circuit. So what you want to do to find the voltage, you multiply these two numbers together. So that's exactly what I'm going to do. So that times your 466.67, and you multiply those two, get two together, and you get 3.94366 volts. So I'm going to switch back to the computer, and I'm going to simulate that and prove that this number is correct. So you've gone through all the math, and what we should get is this number when we switch number 2. So this is SW2 closed. Okay, so let's get back to that. Alright, so here we are again. The circuit's still simulating from earlier, and so we just need to make sure that all these are open, and we're going to check our multimeter again. So we agreed that we're still pretty close to 0, and the only reason it's not saying 0 is because I never put a ground in here. And I can do that real fast, but it really shouldn't change anything. So you want to put a DC ground and just connect it there. Call that good. So now this should read 0. There you go, 0 volts. So we said that we were supposed to read a voltage of 3.94366 volts whenever you close this switch here. So we're going to close the switch, and you get 3.944, which is 366 rounded up to 400. So there you go. We did the math correctly. Using this, you can find the voltage of any of these. Again, what you do is you add up here. So if you want to find the voltage of this switch here, you add these two up together, which would be 250, and you subtract 125 from your 875, and you should get 750. So 750 ohms from this point to this point, and 250 from this point to this point. And you do the same parallel resistance stuff between here and here. So good luck. If you have any questions, I'm available. I should get off of class at noon, I think both days. I think 12:30 on Tuesdays and Thursdays. And I should be down this weekend. So we'll see you later. Thanks. Bye.